Lansbury from
All right. Good morning, everybody. Welcome back. So for this week, we will finish chapter number 6 and move on to chapter number 7. So to start the day, let's have here some quick announcements for this week. So for this week, don't forget to complete the homework, the online homework, chapter 6, part 1, before Tuesday. And for this week, we will not have in-class assignment on Thursday. Okay. All right. With that being said, so let's move on and finish chapter number 6. So we don't have much left. For today, we will talk about how to experimentally measure delta H for the reactions. And we will cover a little bit of fuels and the advantage of each kind of fuel and what's involved when we choose a fuel. Okay, starting here, how to measure delta H in the lab. To measure delta H in the lab, we need to use something called calorimeter. So a calorimeter is basically a block made of stainless steel, for example. Inside this block, there is water, so represented here by the yellow liquid. So there is a stirrer here to make sure the temperature is homogeneous throughout the solution. And inside the water, there is a reaction chamber. So this is all sealed and water cannot get in or out. And inside the reaction chamber is where we will place the reagents that will start the reaction. And here there is also a thermometer to measure the change in the temperature. The energy produced or absorbed by the reaction inside the chamber will be used to heat up or cool down the water. And that's how you know the amount of energy released or absorbed by the reaction. So we will measure uh, what happens with the water in the calorimeter. Remember, if the water heats up, then the reaction is labeled as exothermic because energy is being produced and used to heat up the water. And if the water cools down, then the reaction is labeled as endothermic because energy is being stolen by the reaction from the water uh, to make the reaction possible. A calorimeter is basically anything that has a good insulation from the outside world. So even a Starbucks cup can be used as a calorimeter. Okay, so this is actually a very good calorimeter. The insulation is pretty good here, and we can run uh, any kind of reaction inside the cup, fill up with water, and measure what happens with the water. And that's how a calorimeter works. For the next slide, I would like to show you how to do the calculations, and then we will move on to fuels from there. Okay, so let's switch screens here and then we can move on to the calculations. All right, so let's use a very simple reaction for our example. So it's a basically a neutralization reaction. So we have here uh, an acid represented by H plus reacting with a base represented here by OH minus. And this, as you know, is a neutralization reaction, and the only product, one of the products is going to be water. Neutralization reactions, they have delta H negative. Therefore, that means the reaction is exothermic. Okay, so re exothermic reactions, they produce energy. Energy is going to be released to the neighborhood. If energy is being released, we should expect the temperature of the water inside the calorimeter to uh, rise as a function of the time. Okay, so that's what is expected. So now let's draw a graphic where y-axis is going to be labeled as temperature and x-axis is going to be labeled as time. And here we are going to monitor the temperature of the water as a function of the time. Okay? So starting at time equals to 0, so we start here with an initial temperature. That's before the reaction occurs. When we mix up the reagents, the reaction will start to occur. The reaction is exothermic, therefore the temperature will increase all the way to a point where it will stop to increase. That means the reaction is done and the water is going to reach a maximum temperature that I'm going to label final temperature, or TF. And this is here where the reaction ends. Okay. End of the reaction. All the reagents were consumed. The water heat up and achieved the max temperature. How can we use this data to get the delta H? All the energy provided by the reaction was used to heat up the water, and we have a correlation between energy and variation of the temperature, which I am showing here. And this correlation is Q, that's the amount of energy, is equals to the mass of water times a characteristic of the material that's called CS, or specific heat, times the variation on the temperature, or the change in temperature. The correlation between the delta H of the reaction and Q is that delta H is equals to minus Q. Okay? And that's how we are going to achieve the delta H using experimental data. Units here. Specific heat depends on each substance, and we can find the values on tables. In the international system, specific heat is in joules over kilograms times Kelvin. Change in the temperature. Let's use here the international system unit, which is Kelvin. For mass, the international system unit is kilograms, and energy is going to be given in joules. Yeah, I will not get into too many details here because you guys are going to do this in your lab, and there you can see a little bit more of details. But the message here is that all the heat produced by the reaction is going to be used to heat up or cool down the water, and the calorimeter as well if we are not using an ideal system. And then the correlation between delta H and Q is that delta H is minus Q. Okay, so that will account for the correct sign. Okay, so let's go back to my desktop. Okay, so let's move on. So now I would like to talk about fuels. So this is more of an applied part of thermochemistry. When we consider a fuel, we have to take into account three different things. First of all, is always production cost. Okay, so how much does it cost to produce the fuel? The fuel. Second item is the amount of energy produced. So you want ideally something cheap that produces a lot of energy. So therefore, everybody can buy, and you just need a little bit to get a lot of energy. So that's the ideal situation. And most recently, we also need to consider the amount of carbon dioxide generated when we burn the fuel. The ideal fuel is something cheap that produces a lot of energy and does not generate any or generates a very low amount of carbon dioxide. So let's take a look and compare first the costs. So this graph here, the solid boxes shows us basically gasoline or anything that can be obtained from oil. So we have here production cost on y-axis and availability of the fuel. So see here that what's already produced has a fairly large availability, and it's very, very cheap to produce gas. And that's one of the reasons that we use gas till today. It's cheap. It's really cheap to produce gasoline or diesel, and the availability is fairly large. When we move on to alternatives, as shown here by GTL, CTL, BTL, those are small gases, ethanol, and biodiesel, the availability is much large. However, if we look at the production cost, that is much higher than gasoline or diesel. So that's the downside of alternatives to gasoline. Usually the cost is higher. Okay, so that's the first factor that we need to consider. On the right side of the slide here, I would like to show you a comparison between the CO2 emissions when we compare a conventional car with an electric car. So electric cars are very promising. However, there is a big problem with electric cars that we are going to see here. So let's take a look at the graph. We have here the first two bars are for conventional vehicles or gasoline operated ones, and the last three is related to electric vehicles. The blue bar means the amount of CO2 that is produced when we manufacture and dispose a car. Okay, so again here, for conventional vehicles, we have been doing this for a lot of years. It doesn't take much CO2 to produce and dispose a car. On the other hand, electric cars, they require a little bit more of CO2 in the production and disposal. The next bar, the orange one, is how much CO2 takes to produce the fuel for the car. For conventional vehicles, it takes a little bit less than what's needed to produce. However, that's the downfall for electric cars. Electric cars, we need at some point to recharge. To recharge the car, we need to produce electricity. And if the source that's producing electricity is a 100% coal electricity, for example, look at the amount of CO2 that requires to produce the energy to recharge an electric car. However, if we get smart and move on to renewable electricity, that decreases a lot the amount of CO2 produced to generate electricity to recharge the car. So that's the point I want you to understand. Electric cars, don't get me wrong, they are great. However, we also need to think about what's being used to produce the electricity to charge the car. If we are using coal, that produces a huge amount of CO2. So it's smarter to move on to solar energy or wind energy when possible. Okay, so that will make a real impact. And of course, we also have to take into account the amount of CO2 produced when you burn the fuel. And of course, electric cars, they don't produce any CO2 when running. So that's not going to produce any additional CO2. And here, that's the big downfall when we use gas or diesel. There is a huge amount of CO2 produced. Okay, so That's the advantage and disadvantage when we compare conventional fuels with electric cars. And we can make a quick calculation. You are going to see that the amount of CO2 produced by one car is not that big. However, the problem starts to be huge when a lot of people have car. Okay, so then you will multiply the amount of CO2 produced by a huge factor. So those are the things I want you to understand, and then you can make a more educated guess. You can have a more educated opinion and not just repeat what other people tell you. All right. So now let's take a look at the amount of energy produced by different fuel sources. So we have here a list of different fuels and the energy produced in kilojoules per gram of fuel that is burned. So wood doesn't produce a lot of energy, so very inefficient fuel. If we look here at gas, it produces a fair amount of energy. And the alternatives for gas, for example, ethanol, that produces much less energy per gram of fuel that's burned. Okay, so ethanol, that's a very popular fuel back in Brazil. So we have their cars that are labeled Total Flex, so they can run on gas and or ethanol or a mixture of these two fuels. And because there is a lot of space there and the ideal climate, sugarcane is a very big thing and it's very cheap to produce ethanol. So that's why ethanol is very popular and total flex cars are very popular there as well. So the thing I want you to look here is that gasoline, first of all, is very cheap to produce and produce a lot of energy per gram of fuel. So it's a very efficient fuel. And this is the reason that we still run a lot of gasoline. So everybody wants to have a profit. So it's cheap to produce gasoline and produce a lot of heat. So you don't need too much to run your engine. So that's the reason gasoline is still popular. If you look at the table here, you can see that hydrogen produces a lot of heat per gram of fuel burned. So if you find a way to safely store hydrogen and safely burn hydrogen, you will be really, really, really rich and you will solve the problems of the world basically. Combustion of hydrogen only produces a single product, that's water. So that's the ideal fuel. Produces a lot of heat and the only product produced is water, which is harmless. Okay, so finding a safe way to store and burn hydrogen will solve the world problems on fuel and probably control the CO2 emissions as well.
what happens when you try to store hydrogen and like burn it like right now? Like, why is that so unsafe?
So to store hydrogen, you usually need high pressures because it's a gas at room temperature. So because you need high pressure, it's very, very likely that will leak. And once hydrogen leaks, we have a lot of oxygen in the air, it will explode, unfortunately. So you can look up at the Zeppelin accident. So the Zeppelin was filled with hydrogen, and it's a very, very famous case. Hydrogen leaked and the whole thing exploded. So when you store hydrogen in your car, for example, you have a bomb on wheels, basically. So if you solve this problem to store safely hydrogen, avoiding high pressures, then that's a big step towards using hydrogen as a combustion. Does that answer your question?
Yeah, thank you.
Yes. Okay. And of course, there's a lot of people looking into safe ways to do that. Uh, One way that I'm aware is starting from water. You can break the bond between hydrogen and oxygen in the water, and then you produce hydrogen kind of on demand. And this is a process that is fairly advanced, so we should see something in the next 10 or 20 years come out from that. So using water to produce the hydrogen and then burning hydrogen. So that solves the problem to of storing hydrogen. Instead, you store just water and produces on demand. Very hot topic for sure. Okay, so now that I showed you some different fuels, look always at cost, energy produced, and at the end, amount of CO2 produced, and then we can make uh, some educated decisions. Okay, so uh, let's do an exercise where there is a comparison between gasoline and ethanol, and let's see uh, what is the difference related to energy produced and amount of CO2 produced. Okay. So green fuels have been a hot topic of discussion in the past years. One of the alternatives to traditional gasoline is ethanol. Consider the complete combustion of octane C8H18, the main component of gasoline, and ethanol C2H5OH, shown below. Okay, so I gave you the balanced equations here, and ethane A, if you use the same volumes of ethanol and gasoline, which one produces more energy? And B, if you use the same volumes of ethanol and gasoline, which one produces more CO2? So ethane A, I want to compare who is the more efficient fuel. And on B, I want to compare who is the greener fuel, or the one that generates less CO2. So I will do item A with you, and B you can do later. Okay. So let's switch screens again. Okay, so let's start solving this problem here. Okay, so first thing, let's analyze the equations. So both of them have delta H negative, so that means both reactions are exothermic, as it should be for a combustion. Okay, and The unit here being used is kilojoules per mole. Okay, so the per mole is a very important thing because it correlates the amount of fuel with the energy produced. For the first reaction, it means that 1 mole of C8H18 will produce will produce 5,461 kilojoules. And for the second one, the same idea, 1 mole of ethanol, when burned, will produce 1,367 kilojoules. So that's what we know from the reaction. So right out of the bat, we can see that 1 mole of gasoline will produce around 5 times more energy than 1 mole of ethanol. Okay. However, we need to compare the same volume or the same mass ideally. So let's see how we do that. Okay. So the first step here is the conversion oops, sorry, here, conversion from volume to mass. We are comparing the same volume, however, the volume was not told. So let's consider that we are using 1 liter of gasoline and 1 liter of ethanol. Okay, so let's first determine the mass of gasoline. Density is mass over volume. Density of the gasoline is 0.755 kilograms per liter. We want to know the mass, and we are using 1 liter. Therefore, we have a mass of gasoline of 0.755 kilograms in 1 liter of gasoline. And let's do the same thing for ethanol. Density is equals to mass over volume. Now we are looking at ethanol. Density is 0.789 kilograms per liter. We need to know the mass in 1 liter. Therefore, the mass of ethanol in 1 liter is 0.7889 kilograms. Okay. So I'm getting the mass because I need the mass to know the amount of moles, and then I can correlate with the equation. Okay, so that's the mindset here. So now that we know the mass of gasoline and the mass of ethanol, let's convert the mass in number of moles. And that's going to be our second step. The second step is to find the number of moles. So let's start here with gasoline. I gave you here all the molar masses, all the molecular masses. So let's use them. 114.2 grams of gasoline, that corresponds to 1 mole. In 1 liter of gasoline, we have 0.755 kilograms, which is 755 grams. And we need to know the amount of moles in this mass. Therefore, the amount of moles in 1 liter of gasoline is going to be, see here, 755 divided by 114.2. That's going to be 6.61 mole. And we do the same thing for ethanol. For ethanol, the molar mass is 46.1 grams. That corresponds to 1 mole. In 1 liter of ethanol, we have a mass of 789 grams, and we want to know the number of moles. 789 divided by 46.1, that's 17.1 mole. Now that we have the number of moles for each fuel, we can use the equation to get the amount of energy produced by each one. And that's going to be our third and final step to find the amount of energy. From the reaction, 1 mole of octane produces 5,461 kilojoules. So let's do this correlation. 1 mole produces 5,461 kilojoules in 1 liter, which is what we want to know. Therefore, 6.61 mole, we are going to produce an amount of energy that I'm going to call X. Cross multiplication here. The amount of energy produced by 1 liter of gasoline is going to be, according to my numbers here, 3.61 times 10 to the 4 kilojoules. And let's do the same thing for ethanol. Now, 1 mole of ethanol, look at here, produces 1,367 kilojoules. In 1 liter of ethanol, there is 17.1 mole, and we need to know the amount of energy produced. Again, cross multiplication here, and we are going to get, according to my numbers, 2.34 times 10 to the 4 kilojoules. Minus and minus here. Okay, so for the same volume of fuel that's burned, gasoline will produce more energy than ethanol. And that's one of the big advantages of gasoline. It produces a lot of energy. So that means if you use ethanol, you need more fuel to do the same thing compared with gasoline. However, you also need to look at the amount of CO2 produced by each one. So I'm not going to do it here, so you can do later. Just looking at the equation, see here that each mole of gasoline produces 8 mole of CO2, while ethanol only produces 2. So probably ethanol will produce less CO2. Then it's a balance. Okay. So what do you want to prioritize? The efficiency or the green aspect of the fuel? And that's what uh, people should look into when they talk about fuels and which fuel is the best. So we have a lot of things to look into a fuel before making a decision. Okay. All right. So let's take a 5-minute break. So we will come back at 11:47 and let's start chapter number 7. Okay, I will see you soon. All right, so let's start chapter number 7, a quantum model of atoms. So from now on, we will basically leave all the calculations and we are going to talk a little bit more about theoretical aspects and quantum aspects of chemistry. So let's dive deeper into the atom. Okay, so for this chapter, we have to start talking about waves and energy, and we will go back to the atomic models. Let's talk about the Bohr model and duality wave particle. And from there, we will move on to quantum numbers and atomic orbitals. To finish the chapter, we will talk about, again, the periodic table and the periodic properties, size, ionization, and electron affinity. So that's our agenda for chapter number 7. All right, so let's start from the beginning. So let's talk about waves and energy. First of all, I would like to talk about the nature of the waves. There are two different kinds of waves. The first one is classified as mechanical waves. Mechanical waves are waves that need a medium to propagate. For example, the sound. Okay? So when you play guitar and you hit the string will vibrate. That vibration will vibrate the air around the string that will hit your ears and vibrate the very thin tissue that you have in your ears, and that will give you the capability of listening. So sound is a mechanical wave, therefore it needs always a medium to propagate. The second kind of wave is classified as electromagnetic. Electromagnetic waves are waves that do not need a medium to propagate. Okay, so they can propagate in the vacuum, in the absence of matter. For example, light. So the light from the sun hits the earth because light is an electromagnetic wave. And that's the difference between mechanical and electromagnetic waves. One needs a medium to propagate, the other one does not. Attention, a wave only transports energy, not matter. Okay, so waves are energy transporters, not matter transporters. Any wave has some properties attached to it. The first of them is amplitude, symbol is A. So that's basically the height of the wave or the maximum displacement of the wave. The unit for amplitude is meters. Second is frequency. That's the number of cycles per second, the number of waves per second that is being produced. The unit in the international system is hertz, and hertz is the same as seconds to the -1. The third characteristic of a wave is called wavelength. Symbol is lambda, and it is the distance between two successive identical points in the wave cycle, and the unit is meters in the international system. So if we look at the figure here, the wave starts at the top, goes down, all the way down, and then goes up again and reach the top. The distance between two tops, that's called wavelength. You can also measure the distance between the two lows, and that's also called wavelength. Okay, so look at the wavelength as the distance that it takes to repeat. Okay, so starting here is going down. The distance that takes for the wave to go down again, that's called wavelength. There is a correlation between wavelength, speed, and frequency, and that's the fundamental equation of the waves. Speed, v, is equals to wavelength times frequency. Okay. So let's take a note here, and let's make sure we have everything squared up. Switch screens. All right, so this is the important correlation that I need you to know. Okay, for any wave, mechanical or electromagnetic, we also have to follow this relationship. Speed of the wave, here we are going to use meters per seconds in the international system, is going to be equals to the wavelength in meters times the frequency, which is the nu right here. And frequency in the international system is represented by hertz. Okay, so that's the unit for frequency. Hertz is the same thing as seconds to the minus one, or 1/second. Every time we have a wave, we can use this equation. V equals to lambda times nu. Okay. So let's shift our attention to light, because that's what we are going to use in the future. Any form of light, which is an electromagnetic wave, has the speed equals to 3 times 10 to the 8 meters per second in the air or in the vacuum. So any form of light will travel at 3 times 10 to the 8 meters per second. And that's the highest speed possible. An electromagnetic wave is any sort of wave that has an electric and a magnetic field associated with. So I don't want to get into too many details here. Uh, so what I want to go deeper here is the different kinds of electromagnetic waves. Okay, we can have from cosmic rays all the way to radio frequency, and this very tiny little range here, from violet to red, is what your eyes can see. So you just see a very tiny fraction of the whole electromagnetic spectrum. Below the violet, we have ultraviolet, and above the red, we have what's called infrared. Okay. To use the fundamental wave equation that I just showed you, I want to calculate the frequencies for the violet light and the red light. And let's see what we can get here. Okay. So if we are talking about light, immediately we need to know that the speed of light in the air or in the vacuum is 3 times 10 to the 8 meters per second. What I want you to do here is to calculate the frequency for the red light and the frequency for the violet light. Okay. In the figure, I'm showing the wavelengths for red and for violet. Attention here that the unit is nanometers. Okay, so let's give you a couple minutes and then we will solve together. Okay, so let me start solving this problem and then let's see if you got it right or wrong. Okay, so let's start with the red light. For the red light, according to the figure, the wavelength for red light is around 700 nanometers. First thing is to transform the wavelength from nanometers to meters. Remember that nano means 10 to the minus 9. So therefore, the wavelength for red light is 700 times 10 to the minus 9 meters. Okay, so let's leave like that for now, and then at the end we can adjust. So because red is light, that means the speed is 3 times 10 to the 8. And now we know the wavelength of red light, so we can find the frequency. Speed is equals to wavelength times frequency. Speed of light is 3 times 10 to the 8. Wavelength for the red light is 700 times 10 to the minus 9. And we need the frequency, which is nu. Let's adjust this equation. Frequency for the red light is going to be 3 times 10 to the 8 divided by 700 times 10 to the minus 9. Therefore, frequency for red light, let's see here, it's going to be 3 over 700, which is 0.004 times 10 to the minus 9 moves up as 10 to the plus 9. 9 plus 8, that's going to be 17. We can make this look better. That's going to be 4 times 10 to the 16, 15, 14 unit here, hertz. Okay, so any of the two answers are good enough. So that's the frequency which red light travels around the space. Okay, 4 times 10 to the 14. Now let's do the same thing for the violet. Violet, according to the table, has a wavelength around 420 nanometers. So violet, it's a much shorter wave. First thing is to convert from nanometers to meters. Remember that nano is 10 to the minus 9. So we can leave like that for now. And let's use the same equation that I used for the red light. Speed is equals to wavelength times frequency. Speed of light is going to be 3 times 10 to the 8th. Wavelength of the blue light is 420 times 10 to the minus 9 times the frequency. We are going to get here the frequency for the violet is going to be 3 times 10 to the 8th divided by 420 times 10 to the minus 9. Therefore, frequency for the violet, 3 over 420, that's going to be 0.0071 times 10 to the 17. Okay, so you can readjust this to 7.1 times 10 to the 14 hertz. Any of the two options are good enough. As you can see here, violet light has a higher frequency than red light. If we just look at the wavelengths, red light has a higher wavelength than violet. Okay, so that's the correlation between wavelength and frequency. Increasing wavelength will decrease the frequency because the speed has to be constant and equals to 3 times 10 to the 8. Okay, so I told you at the beginning that waves, they transport energy. Let's think about the different kinds of lights that we have here, from red to violet. Which one do you think will transport more energy or will have more energy associated with? So let's think about one thing. Right below the violet, we have ultraviolet. And right above the red, we have infrared. If our skin is exposed to ultraviolet and infrared, which radiation is going to cause more damage? UV or IR? So if we think about, UV is much more damaging for the skin than infrared. So that means there is some sort of correlation between wavelength and energy and frequency and energy. Okay, so that's what we are going to discuss on Thursday. What is the correlation between the frequency and the energy of a wave, or the wavelength and the energy of a wave? So at this point, I would like to talk a little bit more about the visible spectrum of the colors here, of the light that you see. So in the lower range is the violet and going all the way to the red. So remember that violet plus green gives you blue. Red plus yellow will give you orange, and yellow plus blue will give you the green. Okay? So that's a way to remember the colors. Your eyes are most sensitive to green. For some reason, your eyes are very, very sensitive to green color. And that's the reason why the first computers, the screen was a black background and green letters, because your eyes respond much more to the green color. And that's the reason of the green old computer monitors. Okay, with that being said, I think this is a good point to stop for today, and we will resume on Thursday. Okay, so I will see you in 2 days then.
Question real quick.
Mm-hmm.
For the answer for the violet, would it be 7.1 times 10 to the 14th?
Yes, that's what we have here. Let me see. I think my letter here is not that great, so that's a 4.
Sorry.
Yeah. Thank you. Yes, you are right. Okay. All right. I think if that's all, then you guys are good to go.
I misunderstood what you were saying earlier. Are we having discussion today or?
Yes, we will not have in-class assignment on Thursday.
Okay, so
Okay.
see you.
Thank you.
Bye-bye.